If we look at organic chemical reactions in general, what you find is that they broadly fit into one of three categories. They're either an addition, where two or more molecules come together, they react in some way, and one molecule comes out the end, because all of the atoms which were in the starter materials have ended up in the product. The opposite of an addition can be considered to be an elimination, where one molecule goes into the reaction conditions and two or more molecules come out the end after some kind of fragmentation process. And the third category is a substitution, where two molecules come together, they react with each other, and two different molecules come out the other side. So in this case, we've got an alkyl bromide reacting with water to give us an alcohol, NHBr. So there are two main mechanisms by which substitution at saturated carbon occurs. And the first of these is called SN1. Now SN1 stands for substitution nucleophilic unimolecular, and that means that there's one molecule involved in the rate determining step. So as an example, here's an electrophile, an alkyl bromide. The first step in an SN1 reaction is dissociation of the electrophile by loss of a leaving group. Now, this is a group, in this case bromine, which can leave the molecule with a pair of electrons, becoming Br- in this case. What it leaves behind is a carbocation intermediate. Now, as soon as the carbocation intermediate is formed, the nucleophile can come in and can recombine with it. And what we end up with is a product and a byproduct Br- in this case. Now, what do we mean by rate determining step? Well, there are two steps in this reaction, here and here. And in an SN1 reaction, the first step is slower than the second step. Now, the slowest step in any reaction mechanism is called the rate determining step, because a reaction can only proceed as fast as its slowest step. So it doesn't matter what the nucleophile is doing in this reaction, it can't react to give product until the carbocation has been formed, and that's formed in the rate determining step here. We can think about SN1 reactions as getting on a full bus that's only got one door. Now if we look at this diagram of the bus down here and you're standing on the pavement waiting to get on, you can't get on the bus at the moment because it's full. And there's only one door through which you can enter and the passengers can leave. So you've got to wait until the passenger exits the bus, leaving a hypovalent intermediate where you've got a gap that you can add something else into, in this case you, before you can get onto the bus and give us the product. So you can think of this bus that's got a spare seat as our carbocation intermediate. So the rate determining step in any reaction is important because it's the one that determines how fast the reaction can go. So factors affecting the rate determining step in an SN1 reaction only involve the electrophile, and the nature of the electrophile determines how fast the rate determining step goes and therefore how fast the reaction goes overall. Now we can break down this nature of the electrophile category into two different subcategories. So the nature of the electrophile involves the stability of the carbocation intermediate that we're forming and what we call the leaving group ability of X, and we'll come on to both of these in turn. So if we consider a range of electrophiles, and here we have methyl, primary electrophile, secondary electrophile, a tertiary electrophile, allylic, benzylic, and electrophiles where the leaving group is adjacent to a heteroatom, then we can form a cationic intermediate from any of these just by dissociating them and pushing the electrons towards Br to give us our carbocation and Br-. Now, if we look at the stability of these carbocations, we have methyl, which is the least stable. Primary is still unstable, but slightly more so than methyl. Secondary, we're starting to gain some stability. These two are resonance stabilized. So the allylic cation here is resonance stabilized by pushing the pair of electrons from the pi bond, like this, and then you can push them back on the other side to get back to the original resonance form. We can do the same thing down here with the benzylic cation. So this one has slightly more resonance forms, so we can use the pi system to bounce this cation around the ring to the ortho and para positions, like that, and then back to the original resonance form again. The tertiary cation down here is stabilized by hyperconjugation and the inductive effect, and the two at the bottom are stabilized by the lone pairs, which are on the adjacent heteroatom. So in the case of the oxygen heteroatom, we've got a resonance form that looks like this, and we can bounce back and forth between those. And in the case of the nitrogen substituted electrophile, we've got resonance forms that look like this, and both of those are highly stabilizing. So because the carbocation intermediate of the methyl electrophile is so unstable, this reaction here doesn't happen. And as a result, SN1 reactions with methyl electrophiles do not happen. We can say something similar about the primary electrophile, in the sense that the cation just does not want to form because it's so unstable, so therefore SN1 reactions don't occur. Once we move to a secondary electrophile, the cation becomes slightly more stable, so therefore SN1 becomes possible. And as we move down a series of electrophiles, the more stable the cationic intermediate becomes, the more viable the SN1 reaction is. So if we look at our intrinsic factors affecting the rate determining step, we can say that the more stable cations are more likely to form, so therefore the rate determining step is faster, and if the rate determining step is faster, so is the reaction. So let's look at the leaving group ability of X. What do we mean by leaving group ability? Well, fundamentally, it's the ability of a group to take a pair of electrons with it and leave a molecule, either as X minus, or if X is positively charged to begin with, as neutral X. So if X minus is a stable species, the reaction to form is more likely to happen, so therefore we call X a good leaving group. If X is an unstable species, the reaction to form is less likely to happen, and therefore we consider X to be a poor leaving group. Now if we look at some examples of leaving groups here, and I've ordered them by their leaving group ability. So these species up here are excellent leaving groups, these ones down here are very poor leaving groups. Now if we break the R leaving group bond, we end up with a carbocation R and these species over here. And if we look at just how stable they are, here we have carbon minus, and then we move down through this scale and eventually we end up with ethers, triflates, mesylates, tosylates, iodides, bromides. All of these are very stable anions, they're very stable species, and ethers we know are basically inert. So they're all very stable species. So the better the leaving group ability, the more stable the species it will form when that group actually leaves. Okay, so now we can answer our second question, the leaving group ability of X. Better leaving groups are more likely to leave, so the rate determining step is faster. And again, that makes the reaction faster. So one final note on stereochemistry. So the stereochemistry of an SN1 reaction. If we look at the reaction in detail, the LUMO of this step here is an empty p orbital. It's a carbocation like this. So when our nucleophiles are attacking, the stereochemistry of the product that we end up with at the end of the reaction is determined by this attack here. So OH minus in this case has got two choices. It either attacks the top lobe of the p orbital, and the product that we would get out here is the wedged alcohol, because OH has attacked the top side of this carbon framework. Or it could attack the bottom lobe of the p orbital, and we would end up with the hashed alcohol here. Now, without any extrinsic factors like other chiral centers in the molecule or a chiral environment that the reaction's occurring in, this will give a one-to-one mixture, because there's no preference for OH minus attacking the top lobe versus the bottom lobe. So we'll end up with a racemic mixture of product. So we can say that stereochemical information is lost in SN1 reactions. So if you start out with a chirally enriched electrophile, you will lose that stereochemical information in the product, and you'll end up with a one-to-one mixture of stereoisomers. So that's the SN1 reaction. The other reaction by which substitution occurs at saturated carbon is called SN2. Now, this is called substitution nucleophilic bimolecular, because there are two molecules involved in the rate determining step. Now, if we take the same electrophile as we had before, an SN2 reaction occurs in one step. So the nucleophile comes in, it substitutes out the leaving group, and everything occurs in one step, and this is called a concerted mechanism. And because there's only one step, it has to be the rate determining step. So SN2's like getting on a full bus, only now you've got two doors. All right, so if we look at our bus diagram, Yes, the bus is full, but if a passenger leaves via the front door at the same time as you get on at the back door, it's possible for you to get on the bus. And this is analogous to an SN2 reaction. So you getting on the bus and the passenger getting off the bus needs to happen at exactly the same time. And that will give you a route to your product. So, key factors affecting the rate determining step in SN2. Well, the rate determining step now involves two molecules. It involves the electrophile and it involves the nucleophile. So the nature of the electrophile is important, as is the nature of the nucleophile. Now, the electrophile in this case can be broken down into steric crowding around the electrophilic atom and stabilization of the transition state. And we'll come on to those two things in a moment. So SN2 reactions are concerted. This means that everything happens in this one step. It all happens at the same time. Now if we look at this from a curly arrow point of view, we would draw something like this. Now this is often called a backside attack because the electrons that are coming in from the nucleophile need to attack the backside of the carbon leaving group bond because we're attacking the sigma star anti-bonding orbital, which is around here. So if we follow this through, the nucleophile approaches the back face of this carbon leaving group bond, and as the nucleophile starts to push electron density into the antibonding orbital, the CX bond gets longer, it gets weaker. So eventually we come to a transition state which is halfway between the nucleophile attacking and the leaving group leaving. Okay, so this is the theoretical transition state between those two species. If we push further through the reaction, eventually we will break the CX bond and we will form the C nucleophile bond. So I'll just run that back through again. So back to the start, the nucleophile attacks and the leaving group leaves, and it all happens in one continuous concerted process. So SN2 reactions occur faster on less sterically hindered electrophiles. So if we look at a range of electrophiles with a range of steric hindrance, we have methyl, primary, secondary and tertiary, with increasing steric hindrance as we go up that trend. Let's look at methyl first. The nucleophile attacking the methyl electrophile has plenty of room to get to that sigma star antibonding orbital that's here, because all it's surrounded by are hydrogens, so there's plenty of room to get in there. So we've got relative rates of reaction down here. The methyl electrophile reacts at a relative rate of 1000, and we'll see how this changes as we go along. So methyl electrophiles are very good at SN2 reactions, and in fact they only occur via SN2 reactions. If we now change for a primary electrophile, we've changed one of our groups from hydrogen to an alkyl group, which has introduced a certain degree of steric crowding around here. So primary electrophiles are more sterically hindered than methyl ones, and the rate reflects that. So the relative rate here is only 20, whereas before it was 1000. If we add another group to become a secondary electrophile, we've introduced more steric crowding again, so the nucleophile's got to work harder to access that antibonding orbital. The relative rate now drops to 1, but SN2 is still possible. If we move to a tertiary electrophile, there's simply too much steric encumbrance around here. The nucleophile cannot access the sigma star antibonding orbital, and SN2 does not occur at tertiary electrophiles. You cannot do an SN2 reaction on a tertiary electrophile. So, we can answer the first question. Less steric crowding allows nucleophiles easier access to the antibonding orbital, so the reaction proceeds faster. So the transition state for an SN2 reaction, we saw that before. It turns out it's stabilized by adjacent pi orbitals. So here we're just looking at a simple primary electrophile, and I've drawn this out in 3D here, and here is the transition state. We're halfway between the nucleophile carbon bond forming and the carbon X bond breaking. If we change our simple primary electrophile for something that's got adjacent pi orbitals, the relative rate now jumps from 1 up to 400. And this is because we've got this pi orbital here, which is stabilizing both the formation of this nucleophile carbon bond and the breakage of this carbon X bond. So this is with a simple allylic substrate. If we move to a substrate that's got even more pi orbitals, so this is a benzylic substrate, the rate increases proportionally, so we end up with a relative rate of 1000. And it turns out that the best electrophiles for this sort of reaction are ones which are adjacent to carbonyl groups. So if we have a carbonyl pi bond here, this is so stabilizing in this transition state that the relative rate increases to 500,000. So this is, 500,000 times faster than the equivalent primary electrophile. So we can answer the second question. Stabilizing the transition state makes it lower in energy, and it's easier to pass through, therefore it speeds up the reaction. So the final question is the nature of the nucleophile. So we looked at leaving groups previously, and we said that the more stable an anion is, or the more stable a species is, the faster or easier it will form. So if we look at a series of leaving groups, so here is a theoretical leaving group, because methyl would never really do this, but if methyl leaves as a leaving group, you form CH3-, which is a deeply unstable anion. If we move to hydroxide, hydroxide is slightly more stable than, well, it's a lot more stable than methyl-. If we move again up to chloride, chloride is a better leaving group than OH, because Cl- is a more stable anion than OH-. And if we move up to tosylate, tosylate is a very good leaving group. That's because the anion is so stable. So more stable anions are less nucleophilic. So methyl is a very poor leaving group, whereas tosylate is a very good leaving group. But methyl- is an incredibly strong nucleophile, whereas tosylate is not a very strong nucleophile. So if we follow the trend back, the more stable the anion is, the less nucleophilic it is, and we can move back down the trend from tosylate to chloride to hydroxide to CH3-. And nucleophiles that are CH3- equivalents include things like Grignard reagents, which are incredibly powerful organometallic nucleophiles. So good leaving groups make poor nucleophiles and vice versa. So if we look at our leaving group chart again, okay, so we have good leaving groups at the top, poor leaving groups at the bottom, and that's because the more stable species when they leave were at the top and less stable species are at the bottom. We can now add another arrow where we say that the less stable species that would form if you were to push them out as a leaving group are more nucleophilic because the anion that they form is less stable. Whereas the more stable anions up here are less nucleophilic because they're happier to have that negative charge. So we can now answer our final question, the nature of the nucleophile. Better nucleophiles accelerate SN2 reactions. So we discussed the stereochemistry of SN1 reactions and said that it scrambles. Well, if we look at the reaction mechanism of an SN2 reaction on this chirally enriched bromide, we are aiming for the sigma star antibonding orbital, as we saw before, and we're going to use OH again as our, or hydroxide as our nucleophile. We're going to get backside attack, we're going to push electrons into this antibonding orbital, and we're going to break the CBr bond. So let's see that happening again. And watch the stereochemical configuration as we do this. So the hydroxide approaches, the CBr bond gets longer, starts to break, and watch what happens to the groups around the carbon. They flip out, like turning an umbrella inside out. I'm going to run that back through again. So we'll go back to the start. So as the OH approaches, it flips the configuration of the groups in that molecule. And if you draw this out in the same orientation as you drew out the bromide, you'll notice that the OH group is now on a hash bond as opposed to a wedge bond. So what we've got is complete inversion of stereochemistry, going from the starting material to the product. And SN2 reactions are said to be stereospecific. That's because the stereochemical configuration of the starting material is determining the stereochemical configuration of the product. There's only one option. It has to go via inversion of configuration, so therefore you can't get a mixture unless you've put a mixture of stereochemical configurations in at the start. Okay, so by way of a summary, here's a list of our electrophiles that we've covered in some of these reactions. And let's see how they perform in terms of SN1 and SN2. So methyl and primary alkyl electrophiles will never undergo SN1 reactions. The carbocation intermediates that they form are just too unstable. They will undergo SN2 reactions, however, due in part to the fact that they have very little steric hindrance around them. SN1 and SN2 are possible for secondary alkyl electrophiles. The carbocation intermediates that they form are not super stable, but it's possible, and there's a reasonable degree of steric hindrance around there, so neither of these are great options, but they do occur. For tertiary alkyl electrophiles, SN1 is your only option. You form reasonably stable carbocations due to the hyperconjugation effects and the inductive effects of tertiary alkyl carbocations. And there's simply way too much steric hindrance for SN2 to be a viable option. Allylic and benzylic electrophiles are capable of doing both SN1 and SN2. That's because the carbocation intermediates that you form are resonance stabilized into the adjacent pi systems, and they're also excellent for SN2 because those same pi systems can stabilize the transition state of the SN2 reaction. Now, I said that electrophiles which are adjacent to carbonyls are not very good at SN1. The cation that you form here is reasonably unstable, but mainly the fact is that the SN2 reaction is just so fast that it would be outcompeted anyway, so you would never see the SN1 reaction. And both SN1 and SN2 reactions are possible at electrophiles which are adjacent to heteroatoms. The speed of the SN2 reaction will depend on the steric encumbrance around this carbon, so if you've got any other alkyl groups hanging off of here, then the SN1 reaction you might expect to dominate.